For this lesson, we're going to look at Euler's number and derivatives of exponential and logarithmic functions. So let's start first with exponential functions, because this is going to lead us to what Euler's number is and why it's important. Okay, so we have exponential functions. Let g of x equal b, some base to the power of x. Okay, so we have two options for what might happen. Option one, if we have this, if b is between 0 and 1, then f prime of x is always negative. Now remember that f prime of x means the slope of the tangent line when for any point, given point x. So if we draw a graph, we can see why. So for b less than 1, an exponential function looks like this. It's kind of going downhill, and we can see it has a horizontal asymptote at x equals 0. We can see it's decreasing always, so that would mean f prime of x is always negative. If b is greater than 1, the slope of the tangent is positive. So f prime of x is always positive. And that situation graphically will look like this, where we still have a horizontal asymptote at x equals 0, at y equals 0, but this time we are always an increasing function. Okay, so for bases that are fractions, when we raise them to successively higher powers, they get smaller. For bases that are higher than 1, they get progressively bigger. Okay, so that is an exponential function. So the number e, or Euler's number, and this is the reason actually we don't use e as a variable very frequently, and e is approximately equal to 2.71828. Okay, this is called Euler's number. And that is in fact how you pronounce it. It's not Euler, it is Euler. If you need to, you can Google it. I certainly did, because some of you have made me doubt my pronunciation of Euler. It is Euler. So we have e equals the limit as n approaches infinity of 1 plus 1 over n to the power of n. And we can see this limit, that this is the limit, by just estimating. We're going to take successively bigger powers of n. So if we have n equals 1, we get 2. If we have n equals 10, we take 1 plus 1/10 to the power of 10, which is approximately 2.5937. If we make that 100, we get 2.7048. 1,000, 2.71692, 1 million, 2.71828. And the bigger you get, the more accurate, the bigger the number you plug in for n, the more accurate your approximations of e are going to be. Why is e such an important number for calculus? Well, and it's in fact so important that we have a special logarithm base e that we use. The reason is that the derivative of e to the x is the easiest exponential derivative to find. So generally, we do a lot when we're doing derivatives of exponential functions. We are mostly doing them of exponential functions base e. We're not in this course going to go over how to take derivatives of exponential functions with different bases. You can do it using change of base, but it takes a little bit more. So we are going to stick to functions of base e, and we're going to do the same with logarithmic functions. So the derivative of e to the x. And this is why we like e. In this case, e doesn't stand for Euler. E stands for easy, because the derivative of e to the power of x dx is e to the power of x. E to the x is its own derivative, and that's pretty cool. So if we have the derivative of e to some function of x, then that is equal to e to whatever function of x it was equal to times g prime of x. This is just an application of the chain rule. So these are your derivative rules for an exponential function with base e. And as I said, this is going to be the only sort of exponential function we will be looking at in this course. So let's see an example. Okay. So the derivative of e to the 2x cubed dx is equal to 6x squared. That's the inner derivative times e to the power of 2x cubed. Okay. Example 2, we're going to differentiate e to the 3x times cosine of 2x. So this is a kind of this is a problem we have to unravel a bit because it involves we're multiplying e to the 3x times cosine 2x, so it's going to involve a product rule, but each of our derivatives is also going to involve a chain rule. So we're going to do f prime g plus g prime f. And hopefully at this point you're getting comfortable enough with the product rule that you don't have to write this out. If you do need to write that out, that's still okay. You can still write out what's f prime, what's g prime. So we're going to do f prime, which is 3 times e to the 3x times g, which is cos 2x, plus g prime. That is going to be sine 2x times 2, or negative sine 2x times 2, plus negative 2 sine 2x. So it's the derivative of cos 2x times the inner derivative, which is 2, times f, which is just e to the 3x. Okay, and if you want, you can write this factored out, so we can have e to the 3x times 3 cos 2x minus 2 sine 2x. And I don't believe there is a much simpler way to be dealing with that. There's nothing squared, so we can't do converting it to a cosine squared or something like that. Sorry, cosine 2x or anything like that. Okay. So our natural, we call this the natural logarithm. Logarithm is ln, and you will have a button on your calculator, your scientific calculator for that. And the natural logarithm, ln, natural log natural, is, so ln is equal to log base e. And so we're going to write ln, we're going to be writing ln a lot. So let's look at the derivative of ln with respect to x. So let's let y equal ln of x. We're actually going to derive this. Okay, so if y is ln of x, that means y equals log base e of x. So our base stays the same, y becomes our power, and x is what it's equal to. Okay, so now I'm going to differentiate implicitly here. So I'm going to take the derivative of both sides with respect to x. Okay, so on the left-hand side I get 1, and on the right-hand side I get e to the y times dy dx, or y prime. That's our inner derivative. So y prime is 1 over e to the y. But up here, when we were up here, we said that x equals e to the y. So I can go down and I can replace my e to the y with x. So we get y prime equals 1 over x. Okay? Therefore, the derivative of ln x dx equals 1 over x for all x in its domain. Okay, so ln x, remember, we can only take the natural logarithm of positive numbers. We can't take it of 0, and we can't take it of 1. Negative, anything negative. So no 0, no negatives inside the logarithm function. Okay, so let's take a look here. If we have d ln of g of x, so if we're going to look at a chain rule situation, dx, if you have the natural log of something, it's going to be 1 over g of x times g prime of x. So let's see what something like that would look like. So example 3, we are going to differentiate. We have f of x equals ln of sine x. Okay, and remember, this is only valid for x's that are in the domain of element. So f prime of x, we have to set x greater than 0. So 1 over sine x times the inner derivative, which is cosine x. So f prime of x equals cotangent of x for all x is greater than 0. Okay, let's take a look at b. So let's say f of x equals ln of x cubed plus 3. F prime of x equals 1 over x cubed plus 3 times 3x squared. That's my inner derivative there. So it's 3x squared over x cubed plus 3. So the derivative of ln is 1 over whatever you are looking at. Let's look at one that's a little more fun. So let's say I have f of x equals the natural log of x plus 3 over radical x. So at first glance, you might be thinking, oh no, now I have to do the quotient rule with ln of x. The lovely thing about logarithms is that you can use your log rules to simplify before you try to differentiate, and that can be super useful. You could use the quotient rule, but you don't have to. So let's look at how we might use the log rules to simplify first. So f of x is equal to ln, we're dividing, so this is ln of x plus 3 minus ln of radical x. And we can even take that radical, we can take that one, we don't even have to do the chain rule there because radical is an exponent. So we can simplify that further using the power rule for logarithms. So we have ln of x plus 3 minus 1/2 times ln of x. And that's nice because multiplication by a constant doesn't affect derivatives in the same way that multiplication by a that having a radical would, or having a power inside, because that would cause us to use the chain rule. So now we can take f prime of x with knowing that both of our inner derivatives are just 1. And so that is 1 over x plus 3 minus 1 over 2x. And that makes that relatively simple. And if you had used the chain rule, you would have wound up with something a little bit more complex. Okay, or if you'd used the quotient rule to begin with, chain rule and then quotient rule. So the derivative, so let's take a look at derivative f of x equals ln of the absolute value of x. Because what's going to happen is as we get into integration, we're going to be sort of reversing the process of the derivative. And so what do we do if we have something where the derivative involves x's that aren't necessarily going to be positive? So we're going to look at f of x as ln of the absolute value of x. So that means that f of x equals ln of x for x greater than 0 and ln of minus x for x less than 0. Okay, and the natural log of x still is not going to exist when x equals 0. But the derivative won't exist either because you can't do 1 over 0 either. So now let's see what f prime of x equals. Well, ln of x is 1 over x. We don't have to use the chain rule at all for x greater than 0, and that was what we've been using this whole way along. What about when it's ln of negative x? Well, we are going to get 1 over negative x because that's what our inner function is. Then we're going to be using the chain rule to multiply by negative 1. And this is actually also equal to 1 over x. So for x less than 0. Okay? So we're going to have 1 over negative x times negative 1, which is 1 over x. So actually, the derivative of ln absolute value of x is just 1 over x without any extra complications. So f prime of x, we don't need to write as a piecewise function. It is just 1 over x with the stipulation that x can't be 0.